Hi friends, today I shall be introducing the concept of algorithm analysis, need to analyze an algorithm and the techniques used to analyze an algorithm. But before we talk about analyzing the algorithms, first we quickly see what is an algorithm. Informally, an algorithm is any well defined computational procedure that takes some value or set of values as input and produces some value or a set of values as output. An algorithm is thus a sequence of computational steps that transform the input into the output. Formally, an algorithm is defined as a step by step procedure for solving a problem in a finite amount of time. As an example, we consider the algorithm to find the maximum value in a finite sequence of integers. The input for algorithm is finite sequence of integers and the output of the algorithm is maximum value in the sequence of integers. The algorithm as is shown on the screen is: step 1, set the variable max equal to the first integer in the sequence. Step 2, compare the next integer in the sequence to max. If it is larger than max, set max equal to this integer. Step 3, repeat the previous step if there are more integers, if not then stop. When the algorithm terminates, max is the largest integer in the sequence. All the algorithms have following properties. First, input. An algorithm has input values from a specified set, as for example, in the last algorithm the input is a sequence of integers. Second is output. From the input values, the algorithm produces the output values from a specified set. The output values are the solution. The output in the last algorithm is maximum integer value. Next is correctness. An algorithm should produce the correct output values for each set of input values. Fourth is generality. The algorithm should work for all problems of the desired form. As for example, the last algorithm works on any set of integer values. Finiteness. An algorithm should be composed of a finite number of operations and they should complete their execution in a finite amount of time as in the last algorithm. It should be noted that we should not confuse not finite with very large. A failure to halt usually implies there is an infinite loop in the collection of operations, as in the following example. Suppose we want to write an algorithm to print all the integers greater than 1. Our steps might look like something like this. First, print the number 2, second, print the number 3, third, print the number 4 and so on. While our algorithm seems to be pretty clear, we have two problems. First, the algorithm will have an infinite number of steps because there are infinite number of integers greater than 1. Second, the algorithm will run forever trying to count to infinity. These problems violate our definition that an algorithm must halt in a finite amount of time. Some of the famous algorithms are binary search, quicksort, fast Fourier transform, simplex method for linear programming, Dijkstra shortest path algorithm, JPEG image compression algorithm, Google PageRank algorithm. Next, we see what is algorithm analysis. Consider the following situations. For a given problem, it is quite possible that there is more than one algorithm that represents a correct solution. A good example of this is the problem of sorting. Dozens of different algorithms have been written to solve this problem. Given such a wide variety of solutions, how can we determine which algorithm is the best one to use. Secondly, given an algorithm, can I determine how long it will take to run? The input is unknown and I do not want to trace all possible paths of execution. Thirdly, for different inputs, can I determine how an algorithm's runtime changes? For example, how does the running time changes when a sorting algorithm is given nearly sorted input or a randomly arranged input? How the runtime will change if we double the input size, etc. All this can be answered by algorithm analysis. Algorithm analysis provides estimate for the computing resources needed by any algorithm. Algorithm analysis can also be used for comparing algorithms based on the amount of computing resources that each algorithm uses. Now, what we really mean by computing resources? When we talk about algorithm efficiency, then we are mainly concerned about following two resources. First, CPU time usage, second, memory usage. CPU or time usage or time complexity is the amount of compute time a program needs to run. We care about time complexity to answer the following questions. Can I determine how long the algorithm will take to run? Is the algorithm fast enough for my needs? How much longer will the algorithm take if I increase the amount of data it must process? Say if I double the data items, will the running time be doubled or 4 times or remain the same? Given a set of algorithms that accomplish the same task, which is the fastest one? Space complexity is defined as amount of memory a program needs to run to completion. Question arises, why is this of concern? We could be running on a multi-user system where programs are allocated a specific amount of space. We may not have sufficient memory on our computer. There may be multiple solutions, each having different space requirements. The space complexity may define an upper bound on the data that the program can handle. Space complexity is still important in the field of embedded computing like cell phones, palm devices, etc. The question is then, how do you compare two algorithms for solving some problem in terms of efficiency for both space and time? One approach could be that we implement both algorithms as computer programs and then run them on a suitable range of inputs, measuring how much of the resources in question each program uses. The running time of an algorithm is influenced by several factors. First is language in which the program was written. For example, programs written in assembly language generally run faster than those written in higher languages. Second, efficiency of the compiler that created the program. Third, speed of the machine running the program. Fourth, operating system. Fifth, the size of the input. In fact, processing 1000 records will take more time than processing 10 records. Sixth, organization of the input. If the item we are searching for is at the top of the list, it will take less time to find it than if it is at the end. But this approach of implementing and testing the algorithm is often unsatisfactory for following reasons. First, we must implement the algorithms. This could involve lot of work and it could be error prone also. The same hardware and software should be used in order to compare two algorithms, a condition which is very hard to achieve. It may not be possible to test the algorithms on all possible inputs. We can only test a limited set of inputs. They may not be indicative of the running time for all inputs. It is impractical to determine the running time for some algorithms. for large data sets. For some algorithms, it does not matter how fast the compiled code or the hardware processor is, they are impractical to run with large data sets on any computer. Some of the programs may take too much time to execute, which may run into years. This is true for exponential order algorithms. So, this approach is rarely used. The other alternative is to use some other measure as a surrogate for running time, as we would like to have a characterization that is independent of the program or the computer being used. This measure would then be useful for judging the algorithm alone and could be used to compare algorithms across different implementations. Theoretical analysis of algorithms. One such analysis is theoretical analysis, which measures the efficiency of an algorithm or its implementation as a program as the input size becomes large. It is actually an estimating technique and has proved useful to computer scientists who must determine if a particular algorithm is really worth considering for implementation. The main features of theoretical analysis are: it uses a high level description of the algorithm instead of an implementation. It characterizes the running time as a function of the input size. It takes into account all possible inputs. It allows us to evaluate the speed of an algorithm independent of the hardware and software environment. It gives upper and lower bounds for complexity. Though one disadvantage is the analysis is sometimes difficult and usually works for simple algorithms only. One thing to be noted is that in any algorithm, there are certain operations that contribute most towards the running time of the algorithm. We call these operations as basic operations. The time required by an algorithm is proportional to the number of basic operations that it performs. The time efficiency is theoretically analyzed by determining the number of repetitions of such basic operations as a function of input size. A basic operation could be an arithmetic operation, an assignment statement, comparison between two variables, indexing into an array, reading or writing of primitive types. Deciding on an appropriate basic operation can be a complicated problem and will depend on the algorithm. If searching, basic operation might be comparing two values. If sorting an array, the basic operations might be comparing two values or swapping the contents of two array locations. Sometimes we just look at how many times the innermost loop is executed. Now, the next question is, what does size of input mean? We choose the size to be the parameter that most influences the actual time or space required for the algorithm. The size depends on the problem. For example, if we are searching an array, the size of the input could be the size of the array. If we are operating a graph, the size could be the number of vertices and or edges. If we are computing the nth Fibonacci number or the nth factorial, the size is n. For a numerical problem, size could represent the number of bits needed to represent a number. As an example, for the following problems, the basic operations and input size measures are: finding the exact complexity, f of n, which is a function of number of basic operations of an algorithm, can sometimes be difficult. Also, it should be noted that when we consider the complexity of an algorithm, we do not care about the exact number of basic operations that are performed. Instead, we care about how the number of operations relate to the problem size. This is very important. If the problem size doubles, does the number of operations stay the same or double or increase in some other way. So, what we do is that we approximate f of n by a function g of n in such a way that does not substantially change the magnitude of f of n. The function g of n is sufficiently close of f of n for large values of the input size n. The approximate measure of efficiency is called asymptotic complexity. Thus, the asymptotic complexity measure does not give the exact number of operations of an algorithm, but it shows how that number grows with the size of the input. That is, how much faster will algorithm run on a computer that is twice as fast. How much longer does it take to solve a problem of double input size? Thus, it is more important to determine the most dominant part of the function f of n rather than exact number of operations, since as the problem gets larger, some portion of the f of n function tends to overpower the rest. This dominant term is what in the end is used for comparison. As an example, suppose that for some algorithm the exact number of basic operations is n square plus 27n plus 1005. When n is small, say 5 or 10, the constant 1005 seems to be the dominant part of the function. However, as n gets larger, the n square term becomes the most important. In fact, when n is really large, the other two terms become insignificant in the role that they play in determining the final result. As we can see, when n is 10, the share of n square is only 7.2% in the function, and when n is 100, the share of n square is 72.96% in the function, and as n increases to 1000, the share of n square goes to 97.27%, and for n equaling 10,000, the contribution of n square goes to 99.72%. So, we can observe to approximate f of n as n gets larger, we can ignore the other two terms and focus only on n square. We would then say that the asymptotic complexity of function f of n is n square. Similarly, in the polynomial 8n square minus 2n, we focus on the quadratic term n square, in effect dropping the linear term 2n from the consideration. We can also drop the coefficient 8 because the ratio between 8n square and n square does not change as n grows. For example, if you double the problem size, the run times of algorithms that are n square and 8n square both increase by a factor of 8 only. Thus, the general strategy to theoretically analyze the efficiency of an algorithm as a function of the size of the input n in terms of basic operations is: first, decide on the parameters for the input n; second, identify the basic operations; third, evaluate if the elementary operation depends only on n, otherwise evaluate best, worst and average case separately, which we shall be discussing in next lecture. Next, set up an expression corresponding to the number of elementary operations, and lastly, simplify the expression to get as simple of a function f of n as possible. As an example, consider the following algorithm to find the maximum value of elements of an array. The input for the algorithm is array of n integers and output is the maximum value of array elements. For this algorithm, input size is number of elements in array A, The basic operation is comparison of two elements. The number of comparisons, as we can see, is n minus 1. The simplified form of f of n is thus n. Thus, we say that the asymptotic complexity of the algorithm is n. We consider another algorithm to check if a sequence of integers contain any duplicate number. The algorithm is as follows: input integer array A of size n, output returns true if all the elements in A are unique and false otherwise. The algorithm is shown on the screen. As we can see, for this algorithm, the input size is n, the number of elements in array A. The basic operation is comparison of two array elements. Next, we count the number of comparisons as function of n. As we can see in the algorithm, the outer for loop runs n minus 1 times from 0 to n minus 2. Each time the outer loop is executed, the inner loop is executed as follows. First time I is equal to 0, j grows from 1 to n minus 1, and inner loop is executed n minus 1 times. Second time I is 1, j goes from 2 to n minus 1, and the inner loop executes n minus 2 times. Third time I is 2, j goes from 3 to n minus 1, and the inner loop executes n minus 3 times, and so on, each time executing one less than previous iteration and finally dropping to just 1. The comparisons, which are the basic operations, are made inside the inner loop. Thus, the total number of comparisons equals n minus 1 plus n minus 2 plus n minus 3 going up to 1, which equals n into n minus 1 2, and on simplification and after ignoring the constant term, this reduces to n square. Thus, we say that the asymptotic complexity of this algorithm is n square. With this, we come to end of today's lecture. Today, we had discussed the need for analysis of algorithms and the various methodologies followed for analyzing the algorithms. As discussed, analysis of algorithms is mainly concerned with investigating an algorithm's efficiency with respect to running time and memory space. Time being more critical than space, we have concentrated more on time efficiency of algorithms. The theory developed holds good for both time and space complexity. For measuring the running time of algorithm, the theoretical analysis, which uses a high level description of the algorithm, is preferred instead of implementation. The theoretical analysis characterizes running time as a function of the input size n and takes into account all possible inputs. This allows us to evaluate the speed of an algorithm independent of the hardware and software environment. In the next lecture, we shall discuss some more issues related to theoretical analysis of algorithm. Thanking you.